Hi, and welcome to video 18. In the previous video, we defined what the multiplicative inverse of a matrix is. So we defined the inverse matrix, and we talked about one kind of property or one useful way that it can be applied to solve a system of linear equations. In this video, we're going to discuss more properties of inverses and apply those properties. So we're going to start out with three theorems. We're not going to prove them, we're just going to state them, and then we're going to apply them so we can see them in action. So theorem 9 starts out like this. We're going to let A, B, and X sub I be invertible n by n matrices. We're going to have these subscripts running from 1 through k, those are all real numbers, and P, which is a non-zero real number. Then we're going to have the following 7 properties. First, if I take the transpose of A and I wish to invert it, I can do so. That'll be the same as if I took the inverse of A and then transposed. So it doesn't matter whether I transpose and then invert, or if I invert and then transpose, I'm going to get the same thing, which is kind of nice. Secondly, let's say I have a product, A times B, and I wish to find the inverse of that product. I can do so, but carefully, because this is going to equal B inverse A inverse. So just like we had to change the order when we transposed a product, we have to change the order when we find the inverse of a product as well. Now, this statement here in 2 generalizes to as many matrices as you wish. So this is where X sub i's are going to come in. If I have x1 times x2 times all the way up to xk, and I wish to invert it, that's the same as xk inverse all the way down to x2 inverse, x1 inverse. So whenever you have a product, if you wish to invert it, you may do so, but it's the reverse order of the product of the inverses. The fourth property states that the inverse of the identity is the identity. Number 5 states that if I have the inverse of a matrix and I wish to find its matrix, right? So the inverse of an inverse, that's going to give me just the matrix back again. That makes sense. I'm running out of room, so I'm going to continue over here. So this is our 6th property. And it says if I have A to a power and I wish to invert it, then I can find the inverse of A and raise it to that power. This is really just applying property 3, because if I have, 5 copies of A, so A to the 5th, then it's the same as taking the inverse of A 5 times, just reversing the order. But since they're all A inverse, when I reverse the order, it doesn't, change anything. And the last one, let's say I have a scalar times A, and I wish to find that inverse. So if I know that A is invertible, what's the inverse of 5A? Well, it's going to be the reciprocal of that scalar times A inverse. So if I have 5A and I want to find its inverse, it's the same as 1/5 of the inverse of A. And this makes sense, right? You're essentially taking the multiplicative inverse of the scalar times the multiplicative inverse of the matrix. So we'll do a few examples of applying these in a moment, but let's get all the theorems out of the way first. So we're going to put theorem 10 and 11 on the board next. So theorems 10 and 11 are less list-like and they're more like sentence-like. So let's start out with theorem 10. If A is invertible, then any row echelon form of A does not have a row of zeros. So what theorem 10 is stating is if you use some row reduction on your matrix and you end up with a row of zeros, like we did in one of the examples in the previous video, then that matrix doesn't have an inverse. Theorem 11 is going to kind of springboard off of this. And it states the following. If A is invertible, then its reduced row echelon form is an identity. In other words, if I have an invertible matrix, then it has to be equivalent to the identity matrix. And we can kind of see why this was happening in our methodology of finding an inverse, because in order to find the inverse of our matrix, we had to augment it with an identity and row reduce until we got the identity. So if you can't row reduce to the identity, you're not going to be invertible. There you go. So these are 3 theorems about some properties of invertible matrices. Let's apply them in a couple of examples. For this first example, we're going to basically use theorem 10 or 11 to see, does this matrix have an inverse? So is M an invertible matrix? So to do that, I'm going to start out by using some row reduction and seeing if it looks like it's going to go towards the identity or if it looks like we're going to end up with a row of zeros. So to start out with, I'm going to take the second and the fourth rows and subtract an appropriate multiple of the first row. And I'm gonna, see where that brings me. So I'm gonna do this in one step just to save on some time. So I'm gonna do row 2 minus 3 row 1 and row 4 minus 2 row 1. So this will give me 1, 2, 0, 0. 0, 0, 2, 4, 0, 0, 5, 9, and 0, 0, 3, 5. Next, let's do row 3 minus row 4. There's a reason I'm doing this. Maybe you see it, but let's see what we get. So I'm going to do row 3 minus row 4. So the other rows stay the same, 1, 2, 0, 0, 0, 0, 2, 4. Now these two values are going to stay the same. 5 minus 3 is 2. 9 minus 5 is 4. Then we have 0, 0, 3, 5. Next, I'm going to take row 3 and subtract row 2. So we get 1, 2, 0, 0, 0, 0, 2, 4. And when I do row 3 minus row 2, I'm going to end up with a row of zeros. So then we could continue, row reducing till we're in row echelon form. But once you get a row of zeros, that's a death knell for an invertible matrix. So M inverse does not exist. And I'm just going to say by theorem 10. So theorem 10 says if we end up with a row of zeros, no inverse. Okay, now in the next few examples, we're going to apply many of those properties that were given to us in theorem 9. So that whole laundry list of like 7 properties, let's put a few of those into use. All right, so we're going to do 4 examples of applying those properties from theorem 9. So in these 4 examples, we're going to make use of these matrices here. Notice I'm not telling you A, B, and C. I'm telling you their inverse. So A inverse is the matrix 1, 1, negative 1, 2. B inverse is a 3 by 3 matrix, and the rows are going to be 1, 0, -1, 0, 4, 0, and 1, 0, -3. And C inverse is a 2 by 2. We've got -3, 1, and then 0, 2. So if you wanted to pause this video here and work out these 4 examples, see if you can apply those properties on your own, that would be fabulous. And then you can come back and check in. And then I'll kind of work through them. So example 37, we have A cubed inverse. Example 38 is B transpose inverse. Example 39 is 3/4 of C inverse. And example 40 is the product AC and then its inverse using these matrices over here. So if you want to pause it and work through them, feel free to do so. If you want to do one together, so we'll go through example 37 and then you can pause and try the others. Feel free to do that, right? You know what's going to work best for you to learn. So I'm going to go through example 37. So we had a property that says if I have a to the k inverted, I can switch those two. So I can think of this as A inverse cubed. Now, when we cube a matrix, we haven't talked about any, fancy techniques for it, any shortcuts. So this means we're just going to have to go back to the definition of what it means to cube and multiply those matrices out. So this is going to be 1, -1, 1, 2, 3 times. And then just multiply them out. So this is going to give me 1 - 1, which is 0. 1 + 2, which is 3. -1 - 2, -3. And then -1 + 4, which is 3. And then we're going to multiply that result by 1, 1, -1, 2. And that's going to give me, let's see, 0 - 3 is a -3. 0 + 2, or 0 + 6 is 6. -3 - 3 is -6. And -3 + 6 is 3. So there we go. So notice we didn't have to find A at all. We could just apply that property and get our result. All right, moving on to B transpose inverse. We had a property that said we can switch that as well. So this is the same as B inverse transpose. So I have B inverse over here. Remember, the transpose just says the rows become columns and the columns become rows. So my row of 1, 0, -1 becomes a column. My row of 0, 4, 0 becomes the next column. And my row of 1, 0, -3 becomes the last one. There we go. Oh, that's not too bad, yeah. For example 39, we now have a scalar value times C. We're going to inverse that. When we do that, we have to make sure to find the multiplicative inverse of both items. So namely, we have to take the reciprocal of 3/4, which is 4/3, and multiply that by C inverse. So C inverse was this matrix over here. So 4/3 times -3, those 3's are going to cancel. So I get a nice -4. Times 1 is itself, and times 0 is 0. And then times 2 is going to give me 8/3. There we go. So the trickiest part to a problem like this is remembering to do the reciprocal of the scalar value in front. And lastly, we're going to find the inverse of the product AC. We can do that by finding the product of the inverses, but remember, you have to change the order. So this is going to be C inverse times A inverse. So I'm going to rewrite these over here. We've got -3, 0, 1, and 2. And then we have 1, 1, -1, and 2. So now we just find their product. I'm going to get -3 - 1 is a -4. -3 + 2 is a -1. 0 - 2 is a -2. And 0 + 4 is 4. Okay, and there you have it. So These are examples of applying those properties. How did you do? Did you remember to take the reciprocal here? Did you remember to change the order when you did that? Did you go through the agony of row reducing to find A and B and C and then plug in? Because that would take way longer than applying these properties, right? Okay, so far we have looked at inverses of matrices. Now we've looked at some properties. Ultimately, it would be nice if we didn't have to use row reduction all the time, or if there was a faster way for us to determine if there's going to be a row of zeros, or in fact, if we can determine an inverse at all. In our next video, we're going to be talking about something called a determinant, which helps us to determine it. It helps us to determine whether or not the matrix will have an inverse. So I'll see you next video for that topic. And in the meantime, have a great day.